We started Lewis structures yesterday, no Friday, correct? All right. Today, as part of Lewis structures, we have these three little pieces. We're going to go over them and then put it all together, and hopefully you're okay. Okay. All right. So the first thing we're going to talk about is formal charge. Formal charge only has any application when we do Lewis structures. And formal charge is not that bad. It helps us know which Lewis structure is correct if there are two or more versions that we can do. There are a lot of formulas that have more than one Lewis structure that works. So we have to use formal charge to figure out which one works best. And then resonant structures, in like a 10-second nutshell, is when there are two Lewis structures that work and the formal charges are the same. And then it's like, well, which one is it? And you say it's kind of both. And we'll go over that too. So resonant, so formal helps us decide between two, which one's better. Resonance is when there's two that are the same pretty much, then which one do you choose? You choose both of them. I know some do. And then exceptions to the octet rule. The octet rule means you want 8 dots around everything, but there are 3 main exceptions. Can we have odd? What? Okay, hydrogen and helium, that's true, but we don't say those are exceptions to the octet rule. We say, like, in a structure, when will the central atom not happen? And we say that hydrogen is never a central atom. So that's how I certify it. It's when we have an odd number of valence electrons. We can never have everything be 8 if we have an odd number. Those we don't. And that's when we have too few, and that's when we have too many. And we'll go over all 3 of those. They're not individually too difficult, and even together they're not that bad. So formal charge. Whoops, that's supposed to be way towards the end. Let me just do this. So if we have CO2, and we want to draw the Lewis structure for it, we would follow the rules. We would first count up all the valence electrons that are there total. Okay, so oxygen, the carbon first, I know I said oxygen. It's in family 4, so it has 4 valence electrons. Raise your hands if you're okay with that concept right there. Okay. Oxygen is in family 6, so it has 6 valence electrons, but there are 2 of them. Right? I don't know why that's lowercase. So we have 4 plus 12, which is 16 valence electrons, which is the same as sitting at 16 dots. Who's with me so far? Okay. We kind of have something we can predict right now. We have 3 atoms that have to share 16 valence electrons. Do you think there'll be any double or more bonds? For sure. There's not enough, right? Like you can tell that by the math. They're going to have to share, and there's probably going to be some double sequences. Okay, so carbon dioxide has 2 valid Lewis structures. So we know C is in the middle. Tell your partner the 2 reasons why C is in the middle. Because there's only one of them. So then it has to be in the middle. There's only one of them. And then the other reason it is less electromagnetic. Okay.
Mine was just the dumb version, so I answered.
It's okay. So we put C in the middle, O on the outside. That's rule number 1. We connect them with a line. That's rule number 2. And we complete the octet on the outside. And then if we can't complete the octet on the middle, then what do we have to do? We don't cry. We make double bonds. So here we go. I had 16. I have used all 16, haven't I? Okay, so I can't draw it as written. I have to erase. I'm going to just cheat, but not cheat. I'm going to draw one of the versions. Okay, or I can do one from each side. Both of these meet the rules, right? They are correct, but one is righter than the other. See if there's anything that you think a normal human being should be trained to do by now. Yeah, I don't.
I see nothing.
Every time. Sorry. Okay, moving on. If you're watching the Zoom, I just had a meltdown. It's okay. Okay, so both of these meet the three rules we've learned, but one of them is more right. It's this one is the one that's right.
It's like it's more spread out.
It's not. There's not. Those are all great reasons, but no. The reason why is formal charge. Formal charge. So here we go. Formal charges are used to determine the best Lewis structure when there is more than one valid Lewis structure. So if I said righter, maybe best is an easy way to say that. I like righter. Okay. So we're going to teach you how to do formal charge, so you can then determine which one is the most correct. On the AP test, if they ask for a Lewis structure, they expect you to write the best one. All right, so this is how we calculate the formal charge. We do it for each atom in the Lewis structure. So for each atom, count the electrons in lone pairs and half the electrons it shares with others. Now that may not make sense for a second, but what we do, let me complete these because there's no dots, right? Okay, ready? So what I do, I look at each individual atom, and this oxygen has, look at the screen for a minute, 1, 2, 3, 4 that are in lone pairs. And then it has 5, 6, 7, 8 that are shared. I should say that. It has 4 that are shared. So we take half of the shared ones. So I have 4, and then there was 4 that were shared, so it's plus 2, right? And that equals what number? 6. So far with me? Okay, so this oxygen, it is a plus 6, and you don't have to write these. I'm just doing it for explanation. Well, it's just 6. It really isn't a sign. So yes, technically, but we're not. This isn't a real charge, so that was done. Okay, carbon, like it's not an ion. It's the thing we're using to do this process. Okay, carbon has 8 around it, but they're all shared. So I take half. So carbon is 4. Are we all right with that? Okay, now I'm not done. This is just the first step. And then this oxygen, it's the same as the other one, correct? So it's just a 6. Are you okay with that? Okay, so the first thing is to count the electrons in lone pairs and half the electrons it shares with the others. And then subtract that from the number of valence electrons for that atom. The difference is the formal charge. Now, when we do this one, you're like, this is stupid. Okay? So how many valence electrons does oxygen have? 6. So 6 minus 6 is what? 0. So the formal charge on this oxygen is 0. How about carbon? 4 minus 4 is 0. Oxygen, 6 minus 6 is 0. Okay, so in this structure, the formal charges are all 0. You okay with that? Okay, in this structure, it's going to be different. This oxygen has 1, 2, 3, 4, 5, 6, and then half of 1, right? So, or half of 2. So it has 7. This carbon's still 4. This oxygen, 1, 2, and then half of each one of these, 3, 4, 5. You get how I got those numbers? All the dots, and then 1 for each line. All the dots, 1, 2, and then 1 for each line. So this is a 5. Who's with me? Okay, so here we go. Now, we take this and subtract this number from the number of valence electrons. So I have 6 minus 7. What does that equal? -1. 4 minus 4 is 0. 6 minus 5 is a +1. There are some issues with this formal charge. Well, I don't know. There's one major problem. See, that's the part. You know what the major problem is? It is balanced. They should always add to 0. How I got a +1? Yep. So I'll just draw it over here for a second. I had O, then 3 double bonds. So to find the number of these, I count the dots, 1, 2, and then 1 for each line. 3, 4, 5. And then I subtract this number I just found from the valence electrons that oxygen
Wait,
has.
I'm the only one in here. Gold.
It's supposed to be not minus.
Thank you. Stay out.
Oh, that's a minus. That's a minus. Thank you. And it goes to +1. That's why I put it +1. Okay. The major problem. Anyone know what it is? Well, hold on. Is oxygen happy if it's negative?
No.
Yes.
Yes.
It's electronegative, isn't it?
No.
It would love to be negative. Does carbon care in this relationship? Carbon has no control. Right? It's like, well, okay. Well, what about this oxygen?
It's unhappy.
It's super mad. It's not positive. It would never be positive. This would be a 3 before, or that would be a 3 before that would ever be a +1. So in this formal charge, the way this is written, there's a positive on the most electronegative atom, and that will never fly. So oxygen or carbon dioxide does not form with a triple bond and a single bond. It forms with 2 double bonds, 1 on each side. That way, both oxygens are as close to negative as possible. They're zeros, but both would rather be 0 than 1 negative and 1 positive. Right?
So if it's like if the letters and the elements are symmetrical, then maybe just as a general rule, it should be symmetrical as far as like the electron distribution.
I wouldn't go there. No. Because we're going to get big things that are never symmetrical.
Yeah, but if we ever have to do it for like CO2,
Yeah, definitely. It's linear. Linear, that word, all that stuff.
Wait.
But yes, that would be favored. Where did I lose you? On what he asked me?
Yes.
Then ignore it.
Okay, good.
Because he's right in his head, but I don't want to teach it because it's not always that way. Okay, so formal charge. We'll do more.
so much fear.
But formal charge, when there's more than one option to draw something, you have to do this to figure out which one's the more correct.
Yes, but
Well, that's because I don't get to teach physics.
Just trust me.
Physics is always yes. There's no no's. The chemistry, there's like, yeah, but not
But
this
sort of,
time.
kind of. Not really.
Seth is studying. Everyone say hi to Seth.
Hi,
Hey,
Seth.
Seth.
Can you
Are you
hear us?
watching the video?
Oh, Seth, we're right here.
Seth, you need to be
Can
on.
he actually hear us?
Seth.
Can he hear you?
Seth, not if you can hear us.
10 cousins Seth.
I feel validated now. So, yeah, anyway, and Rebecca's on there, by the way, in case anyone wanted. Hello, Rebecca, how are you today? You don't have to answer, but there you go. Seth says hello. Okay.
Can you see me waving?
Yes, you probably not.
You gotta look at the
You
camera.
gotta come over
Yeah,
right
it's
here.
okay.
Please.
There you go.
Yay!
All right. Okay, you ready? Maybe. Okay, next, we'll come back. Here we go. So here we go. The formal charge on nitrogen in NO3 minus is, okay, based on what we just barely did, see if you can come up with this answer. The formal charge on nitrogen, that's all it's asking you for, is what's nitrogen?
Nitrogen?
What is nitrogen?
No, you said that number minus one. Right? Sorry.
Hi, Austin.
Yeah.
All right, here we go. So I want you to raise the number of fingers, not for the answer yet.
Hey, tell Seth, tell Austin that, Austin should stop, scratching questions.
The what? Never mind. Okay. When we add the things for n, how many did you get? Raise your fingers. Not the answer overall.
This one.
So the first thing you do is add the assign is what they're called, not valence, they're called assign. And it's 4 lines, so you divide that in half, it's 4, right? Everyone get 4? Okay, so then we go valence minus assign. How many valence are there? 5. So 5 minus 4 is positive 1. Oh, that's upside down. Positive 1. Oh, whatever.
That's really nice.
We all right with that? High five. All right, Seth, thumbs up if you got positive 1.
Is this delayed or something?
It must be delayed
By like a lot?
by a lot. It's okay. So positive 1. Raise your hands if you got, okay, no. Speak.
I just have a question. So for the root structures, what is it in family 7?
What do you mean? How do I
How
recognize?
many dogs are going to be there?
For family 7?
Oh my heck.
1, 2, 3, 4, 5, 6, 7. And then you just put like, it'd be over on the other side, technically. So you'd say, okay, the 4 right here, when we calculate the assign, this part right here, count the electrons in lone pairs, so that would be the dots. And then half the electrons it shares with others. So that would mean a line means 2, so you count half of those. So this one had 1, 2, 3, 4, 5. On nitrogen, they were all lines, so just half. 1, 2, 3, 4. Okay. Here we go. I want you to look at this real quick. Will you find the formal charge on all 4 atoms?
I did write it down.
My third one.
Wait, how did I get this? Oh, that's not.
How much?
Okay, 30 more
Wait,
seconds.
hold up here.
I bet Seth is super able to focus in that box.
Oh, yeah. So focused right now.
Nice, Seth. Okay.
Those are good stuff.
They've probably done like 1,000 push-ups today. My kid was in there last year, and he's never been more sore in his life than the day after.
I feel bad. I wrote him a good note. I didn't make him do it.
All right, here we
Seth,
go.
can you hear us?
Barely here. All right, here we go. We ready? So the first thing I'm going to do is I'm going to calculate the assigned electrons. Are we ready? 1, 2, 3, 4, 5, 6, 7. Are we okay with that? If I cut that in half. So I have 7 assigned. 1, 2, 3, 4, 5, 6 assigned. You're okay? We're good. I got 6. Okay. And then this one's the same up here. 1, 2, 3, 4, 5, 6, 7. The next thing I do is I take the valence and I subtract these from them. So, oh, I didn't do beryllium. I'm sorry. How many does it have?
4.
1, 2, 3, 4.
It's okay.
Okay, now I take 7 minus 6, and what do I get?
1.
Oh, no, I did it backwards.
Okay, I'm gonna do it again, right? 7 minus 7 is 0.
Wait.
Okay, then I have 2 minus 4, right? What's that equal? Plus 2. This structure is a disaster.
What is it?
Tell your part negative. Tell your part positive.
Yeah. You also read it upside down, but.
I wrote 0, so. Oh, no. That's
Because it was 2 minus 4. What did I do wrong? Okay, I did fix my mistakes.
So it's
What
negative.
is a disaster about this job?
You don't have enough electrons.
Okay, good. Good, good. All right, what's going on?
Chlorine is positive.
Fluorine's positive. Is that ever gonna happen? Never,
No,
never,
it's
ever, ever.
electronegative.
Because it's the most electronegative. Nothing on the table can make fluorine be positive.
Oh, okay.
What else is the problem?
You have too many electrons.
I have too many electrons because I wrote the wrong one in the middle. This is supposed to be boring.
Oh.
It's okay. It still teaches the same lesson. If I put B in here, some things change, but one thing doesn't, and that's that fluorine, it would be positive and it doesn't want to be positive. So there's one time in our, where is it? Where is it? Wow, I went way out of order. Where are you? Right here. We'll come to. Sometimes, if it's with fluorine, we'll come back to that. We don't try to write this down. When we have fluorine, if we end up with a formal charge that's positive, you just hose over the central atom. Nothing can make fluorine be a positive formal charge. I don't know why I even had that slide right there, because it's super out of order and it's. I didn't have that slide. You guys never saw it. Okay, here we go.
What slide did we not see?
That one you don't know about. Okay, resonance. Now, all parts of these are going to come back today. So don't think, oh man, I'm supposed to know formal charge now. Kind of like that video on how you refer yourself. How many felt comfortable on their ability to refer themselves on whatever it's called?
That is so dumb.
I don't understand how.
Why are we gonna make a
It'll work.
video?
I'm not saying it won't work. just the training, they're like, show them this 2-minute video and be fine. And I
I
watched
feel like
it,
you're
like,
gonna get less kids
Well,
going.
that time
no one goes to
priority-
meantime right now.
Who
So
checks
you
their
can't get less than
emails?
0.
Well, I go to somewhere every day.
They're, yeah.
The thing is they're gonna really use the high priority thing, like, oh, I really need to be at this class when I need to.
Yeah.
I need to go to seminary.
Yeah.
You have no idea.
Ozone is O3. If we draw the Lewis structure for ozone, we end up with this. Now, don't worry about it. Like, you didn't even draw it. You don't have to know what it is for ozone. But, is that the only way it could be?
Be the mirror.
Could be the mirror. We could have 2 O and 1 O.
You could have 2 double bonds. But
You
you,
know, wouldn't have 2 double bonds. But how do I know, in this class, how do I know whether to put the double bond on the right side of the central or the left side? You don't. And they're no different, right? So this is what we call a resonant structure. Both of those are accurate. And if you actually look at ozone and study where its electrons live, they don't live on one side. They sort of live on both. Because electrons are moving, right? So a double bond just means that there's going to be 4 electrons in this area. But could they at one point in time have gone over there? Absolutely. So this is what we call a resonant structure. When 2 Lewis structures are basically the same, we accept a hybrid of both. So, yada, yada, yada. This is kind of what I was about to say.
Wait,
What?
I'm confused.
That's fine.
And Seth says he's confused too.
Okay.
So,
What are you confused about, Abby and Seth?
oh, that's why he was texting.
Abby was his voice right
I mean,
Seth is a great left-handed texter.
that's impressive.
For real though.
Are you left-handed?
He says he just can't hear very well.
Okay. Well, let me keep going. Let's see if it helps to make sense.
That's something I
Here we go.
think is like earbuds or something.
Because, oh, I need headphones for the Chromebooks that you get from a
Okay, here we go. So this is at odds with the true observed structure of ozone in which both O to O bonds are the same length. We learned a couple days ago, this one should be short. And this one would be long, right? Because a double bond is shorter than a single bond, remember that? So when you look at it, you should see short and long, but when they look at it, they see that they're the same.
So, like,
Right.
Both of them have like 1.5.
They have 1.5, which is kind of crap. They, at any given time, they're gonna have both on one side or the other, but they're constantly moving. So there's no defined thing, they call it a continuum. So, it's all right, keep going. So one Lewis structure cannot accurately depict the molecule of ozone. We use multiple structure resonant structures to describe the model, or we use O. Chevron. There's your keyword.
So they like share the double bond?
Sort of. It's just, it can move. Electrons are moving around all the atoms. At any given point in time, the 2 pairs that they share can be on the left or the right. Okay, so when we have multiple things that work the same, because they are the same, they're just a mirror, right? We combine them and make them what we call a resonant structure. Now, there's 2 key words that are important: resonant and delocalized, which we've talked about before. What else had delocalized electrons?
Metal.
Metals.
Oh, yeah.
Okay, so look, just as green is a synthesis of blue and yellow, our resonance structure of ozone is a combination of both. Kind of out of that? Like we say, ozone is this, it's both of them mixed. This right here, 1, 2, 3, 4, 5, 6. This is cycloheptane.
Fancy.
It would be, if we drew it out. No, that's gonna be off. The double bonds would be like this. Or they could have been here. Both of those are the same, right?
Which direction can this go?
Yep, so we call it a resonant structure. We just put a circle in the middle.
That's why there was an O.
That's why there was a O. It represented that it was a resonant structure. That the electrons are really anywhere in that ring at any point in time. Okay, so here is SO3. Will you draw its Lewis structure? A lot of you are going too many valence electrons. I don't think so.
Well,
No.
I'm kind of.
It's okay. So I kind of think I know what all of you are doing. No.
Oh. Holy cheese and crackers.
That's what I have to look.
I had crackers.
Okay, well, let's follow our rules and see what we get. All right. So we have SO3. How many total valence electrons do we have? 24. You okay with that? I put sulfur in the middle because 1 is the only thing that is 1, so it must be in the middle. How do I get 24? Is that the question? Okay. So then the next thing I'm gonna do is complete the octet. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6.
So I have the right thinking. I just.
Now, I'm not done, right? Go ahead.
What do you mean?
I mean, the most electro things get 8 dots around it. So the line counts as 2 dots. Okay. Now, life is great for oxygen, but have we completed sulfur yet? No. And oxygen's mean, but it can't boss sulfur around that much. So we've used up all 24 though, right?
Oh.
We've used up. And I don't know if this will click for anyone, but you could look at this number and that right there, and you would know I'm gonna have a double bond. Because you can't octet 4 things with only 24 valence electrons. Okay, here we go. So in order to octet, I need to erase at least one pair and draw a double bond. Does sulfur now have an octet?
Yes.
Yes. Do all the oxygens have octets? Yes. All right. Or you could have put it here. Or you could have put it there. So is this a compound that has a resonant structure? Yes, it is. Go ahead.
How would we draw that? Like for the
Most likely, it would ask you to draw one. And this is like 99% how it does. If they draw SO3, and the next question would say, does it have a resonant structure? You don't have to draw. All of these would be acceptable. And then you say, yeah, SO3 does have a resonant structure. What's wrong? I see the eyes. Are you good?
I'm good.
Okay. Now, if you were forced to draw this, you really only have to draw one. But you could, if someone felt like it, you could draw them like this. But you don't have to do that. What's that? Can I try another one?
Yeah, let's do.
I don't have them all memorized. I don't even know another one. I'll look one up in a minute. But before that, oh, there's one. There we go. You want to try it on your own? I think it was the H, was it 3 L's? Well, we'll just cheat. We'll just talk through it. All right, HCO2. What do we call that? You remember? Hydrogen carbonate. Good. Okay, so here we go. Like these are the answers, but I'll draw and talk you through it. Sound good? We would pick carbon as the central atom. It would have just been HCO2 -1. It would have said, draw the structure for hydrogen carbonate. This would be technically hydrogen carbonate. I don't know, this is kind of messed up, but it's a thing. We're okay. Okay, so I would have to choose C as the central atom for 2 reasons. One, it's less electronegative. The H is the least, but H can never be the central atom. All right, then I would put things on 3 sides. I would have put angles because I wouldn't have known better, and it doesn't matter yet. H, O, and O. Don't worry about the bends. You can put the structure however you feel like right now. Then the next step, I really should have calculated how many valence electrons I had, right? So I have 1, 4, 6, and 6. Those are the valence electrons. Right of that. So I have how many? 17 plus 1. Remember that little nugget? If it's an ion, you add for each minus and subtract for each plus. So I have 18 valence electrons. Okay, complete the octet. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now life would be good if everything works out. 2, 4, 6, 8, 10, 12, 14, 16, 18. I did something wrong. What did I do wrong? Oh yeah, I haven't octeted carbon yet. Yeah. Okay, so I've met 18, good, but I have not met the octet for the central atom. So then we would erase, pretend these don't exist, and we put a double bond. Or we would pretend these didn't exist, and we put a double bond. Either one of those would be correct, right? So we would say if we wanted you to draw that. Yeah.
When you do the fancy little angle thing that represents both of them, what do you do with the electrons? Like the dots.
You still just count them as 2.
Yeah, can you draw one of those with like that being used?
So like SO3.
Or no, just draw like
Oh, just this?
HCO2
So
with the
H,
angle thing.
C, O. And I have my O. And we'll pretend it's the bottom one. No, yes, we won't. We'll go like this. We still have,
All right, just pretend like it's both of them.
right.
Right.
Okay, enough on that. This is what we were talking about before. This is where you'll see a circle. These are called benzene rings. They're really bad for your body. The organic compound benzene, C6H6, has 2 resonant structures. Is commonly depicted as a hexagon with a circle inside to signify the delocalized electrons in the ring. Delocalized electrons are electrons that move. In metals, they are free to move wherever they want. That is not true here. They're allowed to move from one side of the central atom to the other. So that is different than how metals are. All right, so whatever. Okay, the third nugget for today was exceptions to the octet. They're not all. One of them's super easy. One of them's super rare. And the other one's in the middle. Okay, there are 3. Now, I'm not going to be on here very long, but all 3 of these things are on the top of the slides that talk about them also. So the 3 exceptions to the octet rule is when you have an odd number. These are rare, but when you have an odd number, you can't complete the octet on the central atom. The central atom is the one that always gets hosed in the exception because it's the least electronegative. It has no say in the relationship. Okay? Ions are molecules with less than an octet. We did this one way out of order. And then with more than 8 valence electrons, and that happens with an expanded octet, and they're pretty easy. When you get to the D's, then we can go to 10. We can go to 12, because we're messing with the D block. All right, Seth is having the best time of his life. Good question. There's still a lot to be understood about chemistry with the F block. Okay, so here we go. Though relatively rare and usually quite unstable and reactive, there are ions and molecules with an odd number of electrons. Nitrogen monoxide is the #1 example here. When we go to draw this, it's these 2 atoms. Nitrogen has 5 valence electrons. Oxygen has 6. 5 plus 6 equals 11. Now, usually nitrogen and oxygen makes polyatomic ions with a charge of -1. Why are they doing that? Why do N and O combinations always want an electron?
That's the short one.
They're short one. They're odd. They don't like being odd. They get an electron from a metal, form an ion, a polyatomic ion, and then bond. So they're rare, but here we go. Since there is only 11 valence electrons, you have to leave one of them without 8. And who's going to lose that battle? The less electronegative atom. Every time loses the battle over who gets the electron. These are really rare, but they do happen. You don't have to spend a ton of time on them. Complete the octet for sure on the more electronegative atom, which is almost always oxygen, and then leave the other one short. Yeah. What's that? If I put a hydrogen on there, then I'd have, what would we call that? Hyponitrous acid is what I would have. And it's fine. It would act like an ionic compound. And it would be happier. Okay, now fewer than 8. This is what that other slide was. There we go. That screwed up. BF3. And I'll just tell you, this is on my test. And if it's tested, it's on the AP test almost every time. The main one that is fewer than 8 is almost always BF3 because fluorine is a bad. Okay. Consider BF3 giving boron a failed octet places a negative charge on the boron and a positive charge on fluorine. And that will literally never, ever happen. Boron cannot steal fluorine's lunch. This doesn't work that way. All right, so it would not be an accurate picture of the distribution of electrons in BF3. So the one that is this version, where you leave the octet of boron at 6. But you complete the octet on all 4. It is pretty much the only one. So if you see BF3, that's your red flag that, oh, that's the one where the central atom only has 6 valence electrons.
So pretty much just go with whichever one is the less electronegative, and that one loses the electron.
Yep. Now, this is one of the only times where it is covalent and the octet rule is broken. Because even fluorine, it doesn't share anyway, it just steals. But boron's just barely electronegative enough that they do have to share, but they're not going to share either.
So on that one, there's 7 dots on the floor, is it 6, because each line counts for.
Yeah, if I did that, I was a mistake. I'm sure I drew the 7 and then drew the line. Yeah, it should not. Okay, you all right with that? So far, odd. No reason, because you add them up and you have an odd number of valence electrons. Complete the more electronegative, don't complete the less. And then boron trifluoride, it's almost always the same one. Fluorine will not be a positive ever. If you ever do a formal charge and it's a positive, there's your problem. All right, so there again, once you go, the most important version of BF3 is the one on the left. So the lesson. If filling the octet of the central atom results in a negative charge on the central atom and a positive charge on the more electronegative atom, don't fill the octet of the central atom. This happens with fluorine, maybe oxygen sometimes, but that's about it. Don't ever let fluorine be. Okay, and then the last one is really a piece of cake. If you look at PCl5, there's a central atom, and there has to be 5 things around it. So there's not an option to only have 8, right? So it uses the D shell and form up to 5. These are not too bad. These are the most common for sure. I'm not saying. Okay, the only way PCl5 can exist is if phosphorus has 10 electrons around it. It is allowed to expand the octet of atoms on the 3rd row or below. Because, you can see the question you asked, it says, presumably, D orbitals are used in the bond. So there's still not enough agreement that that's even how it works.
So for PCl4, it would be the exact same thing, except just 5.
Yep.
Okay. So just choose which.
Okay, so even though we can draw a Lewis structure for phosphate ion, PO4-3, it has only 8 electrons around the central phosphorus. The better structure puts a double bond for the phosphorus and 1 on the oxygen.
Does phosphorus just want to have 5 then?
Doesn't like want to have 5, but in situations where it can not be a positive, it would prefer to do that. So this structure here, there's no positives, which is really the goal. And so this one would be the more accepted. They do not test this one on the 8th test. Okay, here we go. Draw the following Lewis. All right. Someone take a picture and put it on the group so you know. Try and work on these. We will go over them tomorrow. Can someone tell me why NO2 has a -1? It is. Whoever said because it was odd, that's what I was looking for. It can get one Now it's even, and it can complete the octet. Then take a picture of that. I'll go back to second. Okay. Try these. I will go back to the previous slide. And if you want to know the answers, that's really bad. We'll go to the end of the video. I'm just going to pass them already going out. All right, my friends. It's been a great time. Seth, it's great to have you. We've been for a while. How you doing? I just pray.